Good morning, class, and welcome to this lesson on Newton's third law again. But now we're going to be looking at a little bit of math involved with Newton's third law. Unlike our last lesson, we uh, we looked at Newton's third law from a very conceptual standpoint. If I push on this, it pushes back on me with the same force. When my feet push backward on the ground, the ground pushes forward on my feet. So that was a very conceptual look at Newton's third law. Now we're going to do a little bit of math. So there's really with Newton's third law, it comes in a lot of different ways, and I'm going to keep it pretty simple on this lesson. There's one basic problem that recurs in AP Physics, and it's a situation where you either have two people or two objects. So I'm going to go with people for right now. We have two people or two objects, and they're standing facing each other, and they're usually always wearing like skates or rollerblades or something. And the skates or the rollerblades are supposed to kind of indicate to us that they are on a frictionless surface. You're going to find a lot in this class for right now. We're going to assume everything is frictionless just because it makes the math so much easier to start off with. So they're on a frictionless surface and they're holding on to each other and then they push off from one another. And they're usually different masses. So we have a situation where, let's say this is the guy and he's 100 kilograms, and this is a girl and she's 50 kilograms. Okay? And they push off from each other. And when they push off from each other, it'll say like the man pushes with a force of, we'll say, 75 newtons. What is the acceleration of each? What is the acceleration of each? And that includes direction. So we have to find how fast these two are accelerating. So now that we know they're accelerating, we have to look at this, and because they are a action-reaction pair, okay, action-reaction pair, he pushes with a force of 75 newtons this way. She's going to push with a force of 75 newtons that way. And then so we have to look at the man first. So man, F net equals MA. So 75 newtons equals 100 kilograms times A. Solve for A. 75 newtons over 100 kilograms equals A, which is just 3/4 meters per second squared. And then we're going to do the female. F net equals MA. 75 newtons equals 50 kilograms times A. So 75 newtons over 50 kilograms equals A, which comes out to be 3/2 meters per second squared. So you can see here that the woman, because she has a smaller mass, is going to be moving or accelerating faster than the man. Remember, we said before, we have F equals ma. If you have a larger mass, you're going to have a slower acceleration, and if you have a smaller mass, you're going to have a higher acceleration. So this really is the basic problem. Now, we didn't give direction, so this man is moving. She pushed. If we have a typical XY coordinate system and we call right positive, this is X, Y, and we call this way positive and up positive, and then left negative and this negative. This woman, even though she's going backwards, is moving in a positive direction. So her acceleration is 3/2 meters per second squared in the positive direction, or east, if you want to use the cardinal system. And the man is moving to the left, so it would be 3/4 meter per second squared west, or negative, because he's moving in the opposite direction. Equal and opposite forces. Okay, so that's really it for Newton's third law, using applying it to a math problem.